Hello, today we'll be talking about thermodynamics, more specifically heat engines and refrigerators. Thermodynamics is a branch of physics that studies the transformation of energy. Let's take a look at the laws of thermodynamics. Boy, is it getting hot in here. The first law has to do with the change in thermal energy equals the amount of thermal energy transferred plus work done by external forces. It can also be written as Q equals work done by the system plus the change in energy, which means that work done by external forces equals the negative work done by the system. Any energy transferred into a system as heat is either used to do work or stored within the system as increased thermal energy.
The second law of thermodynamics is that most macroscopic processes are irreversible. As shown on the diagram on the left, heat energy is transferred spontaneously from a hotter to a colder system, but never from a colder system to a hotter system, as shown on the diagram on the right.
Okay, so a heat engine is anything that transforms heat energy into work. So a simple kind of diagram would be Q is coming in and it transforms it into work. So this is work and this is Q, a pretty Q. And then thermal energy is released. So there always has to be a release in thermal energy to keep the heat engine moving in a kind of cyclic fashion. So an example of a simple heat engine is this. So here fuel is burned to create pressure and lift the mass so that gas does work. And here isobaric expansion just means that the gas does work at a constant pressure. And then here the mass is gone and it cools back down. And it's going down on isothermal compression. That just means that energy doesn't change, but that's ideal. Thermal energy does change, so energy does change going from heat to work.
An engine's thermal efficiency is the measure of how good a heat engine is at transforming heat into work. And this is shown by this equation. So thermal efficiency equals work out over QH. And work out is the work done, and QH is the heat required. And no heat engine can have an efficiency of 100% and be a perfect engine. I feel lopsided though. Okay. Work out equals Q net, which also equals QH minus QC. Work out is the work per cycle done by a heat engine. Now let's cool off with a question. What, if anything, is wrong with this refrigerator?
What?
To conserve energy, the heat QH exhausted to the hot reservoir would be equal to QC plus the internal work. And this would be 40 joules plus 10 joules, because 10 joules and 40 joules, and this would be 50 joules, not 30 joules. So this would be appropriate to a heat engine if the energy transfer arrows were all reversed.
Now let's talk about the Carnot cycle. The Carnot cycle is a perfectly reversible cycle, which makes it impossible to obtain. The Carnot engine has the maximum possible thermal efficiency. The efficiency of a Carnot engine depends only on the temperatures of the cold and hot reservoirs. So This first equation is the efficiency of the Carnot engine equals 1 minus the temperature of the cold reservoir over the temperature of the hot reservoir. So, the Carnot engine has a maximum possible coefficient of performance. And the second equation shows the coefficient of the performance equals the temperature of the cold reservoir over the temperature of the hot reservoir minus the temperature of the cold reservoir. Because Carnot heat engines and Carnot refrigerators are not possible in real life, the thermal efficiency and coefficient of performance of Carnot engines are what real engines and refrigerators are compared to.
A refrigerator is a heat engine in reverse, using work to pump energy uphill from cold to hot. Air conditioners are also considered refrigerators.
So this is the energy transfer diagram of a refrigerator. So the amount of heat exhausted to the hot reservoir is larger than the amount of heat exhausted from the cold reservoir. External work is used to remove heat from a cold reservoir and exhaust heat to a hot reservoir. So conservation of energy is of course applicable to refrigerators, so the change of thermal energy equals 0. And so conservation of energy requires that QH equals QC plus work going into the system. These are the equations.
Oh no! The AC is broken. Should we use the refrigerator to cool off?
No! So to conserve energy, QH has to equal QC plus work. More heat is going to come out of the back than the front. It's going to be hotter.
An energy reservoir is an object or a part of the environment so large that its temperature does not change when heat is transferred between the system and
Hi, I'm Alexandra Marianopoulos, and today I have the pleasure of sharing with you a song I wrote in the 3rd grade. Please note the 3rd grade, okay? I'm sharing this for a physics video, so. My fridge, refrigerator keeps my food cool till I come back later. Got ice in the back so it don't heat up. Everything's cold in my fridge, yup. After a feast, my fridge is full. There's food piled high and it never looks dull. Everything's delicious and it never goes bad. If my fridge ever broke, then I'd be real mad. My fridge, refrigerator keeps my food cool till I come back later. Got ice in the back so it don't heat up. Everything's cold in my fridge, yup. After a game, I want a cold drink. I put water in my fridge because it's colder than my sink. Take out a glass, pour a cup of juice. Milk in my cereal, even chilled fruit. My fridge, refrigerator keeps my food cool till I come back later. Got ice in the back so it don't heat up. Everything's cold in my fridge, yup. My food is protected in my kitchen hall in a big gray box that I plug in the wall. I call it my fridge, I wouldn't touch it. I got cameras all around and I'll get ya. My fridge, refrigerator keeps my food cool till I come back later. Got ice in the back so it don't heat up. Everything's cold in my fridge, yup. Oh!
Today we'll be talking about thermodynamics.
Oh my
Hello and welcome to our lesson. Today we will be talking about thermodynamics, more sophisticated. Can't do this. Okay. Are you recording this whole thing?
Just now? Come on!
Okay.